Assalamu alaikum, dear students. Today we are going to learn about soil index properties. It's week 8 and lecture number 16 of Geotechnical Engineering 1. So let's begin the lecture. So what are the soil index properties? Index properties are basically the properties which helps you identify or classify the soil into a different groups for the use in different engineering purposes. Now, if you have two different types of a clay, that is possible, because if you have clay, it will not be always of the same type. Similarly, if you have gravel or aggregate or sand, it will also not be of the same type all the time. So to distinguish one particular type of clay from another clay, or to distinguish one particular type of a sand from another sand, the properties required for that purpose will be the soil index properties. These properties will determine if particular sand is different from any other sand, or if particular clay is different from any other clay. So, for coarse grained soil, which are non-cohesive, coarse grained soils are sands and gravels, because they do not possess any cohesive forces. They only have coarse grained particles, so there is no cohesion in the particle. So that's why they are also known as non-cohesive soil, as we discussed earlier. So in coarse grained soil, which are typically sands and gravels, the index properties are particle size distribution. So it depends on the particle size distribution as well. If there are larger size particles in greater quantity, or if there are smaller size particle in greater quantity, or if all the particle are of uniform size, or if all the different sizes are available, then we can distinguish one particular soil from another. Like in previous lectures, we already discussed about well-graded sand, well-graded aggregate, poorly graded sand, or uniformly graded sand, etc. So in that, you know that every material was different from another. Some material was uniformly graded sand, some was well-graded sand, some was like gap-graded aggregate or sands. So according to particle size distribution, you can say that different types of aggregates are different from each other. Okay, so on the basis of that, you can determine if the particular aggregate is a coarse aggregate, or the particular aggregate is a fine aggregate. So if this particle sizes are smaller, it will be fine aggregate. If it is particle sizes are larger, then it will be coarse aggregate. So you can see over here there are two different names, coarse aggregate and fine aggregate. So they are both aggregates, but one is coarse aggregate, one is fine. So you can distinguish, or you can differentiate between the two based on the particle size as well. The next is particle shape. In coarse grained soil, in the previous class we discussed that we have got different particle shapes. There are bulky particles, there are flaky particles, plate-like particles, there are needle-shaped particles. So if you have like aggregate with you in which it is sourced from a crush plant, so you will see that the shape of the aggregate will be more angular. Okay, so you can call that as an angular aggregate. While if you get aggregate from a riverbed, in that case you will see that aggregate is more round in shape, and you can call it a round aggregate. So based on the particle shape as well, you can differentiate between one soil and another soil. So that's why particle shape is also very important index property. Then you have relative density. We already discussed about relative density. So if the relative density of a soil is high, more than 80%, then it is known as dense soil. Like if you have a sand whose relative density is greater than 80%, then you can call that as a dense sand. But if the relative density of sand is like the same sand with same particles, same particle size distribution, but if density is less, if it is not compacted, and if say its relative density is 30%, then it will be called as loose sand. So once again, on the basis of density, you can differentiate between a particular soil being different from another soil. So one can be dense sand, another can be a loose sand, just because their relative densities is different. Then the next important property is the consistency of the soil, which we will be discussing today. So I will talk about detail in about consistency of coarse grain and fine grain in the coming slide. But based on consistency, you can say that a particular soil is different from another soil. Then we have clay and clay mineral content in the coarse aggregate or non-cohesive soil. If the clay is present inside, or if the clay is present, then what type of mineral clay is present there. In the previous lectures, we discussed about montmorillonite and elite and kaolinite. So these were the various mineral forms of a clay. So if the clay is present, that will also affect that if soil is different from another soil. If it is a clay sand, it will be different from sand, because in one you have got clay, and the clay will affect the properties, the engineering properties of that soil. So sandy clay or clay sand will be different from sand, pure sand. So that is why, based on clay content and clay mineral type as well, one soil can be different from another. Now coming to fine grain soils. Okay, fine grain soils are cohesive soils like clays, commonly where clays are cohesive. Their index properties are their consistency, okay, which I am going to discuss in the next slide. Consistency is the resistance to shear. So that will basically tell you if your particular clay or particular soil which you have taken from any source is different or similar to any other soil. Then obviously in cohesive soil we will have clay, but its clay mineral content will be also very important. Okay, the montmorillonite will have different behavior than elite or kaolinite. We will discuss them in great detail later on while discussing shear strength and compressibility of those soils as well. Specifically speaking about montmorillonite, that they are called expansive clays. They have potential to expand and contract, like here in this picture you can see. Upon drying, this soil has developed a lot of cracks. So this is typically a property of montmorillonite, that it can change its volume a lot upon wetting and drying, which is usually problematic for your buildings, infrastructure, etc. If you change their moisture content, if you provide them with water, they will increase in volume, but if you dry them, their volume will reduce drastically, and that will basically result in shear in settlement, shear strength loss, etc. There is a lot of problems which is basically caused by the volume changes, which we'll be discussing in detail in this course as well, and your coming course in Geotechnical Engineering 2 and the foundation design as well. Then the next property which is very important for a fine grain soil is moisture content or water content. Okay, you can see over here as well, upon drying this clay soil, it has developed all these cracks. The volume changes has occurred. Similarly with moisture content, with the water content, its consistency will be also affected. Its shear strength resistance, it will be a shear stress resistance will be also affected as well. So moisture content or water content is also very important index property for fine grained soil. Okay, in coarse grained soil it does not affect its property that much, but in fine grained soil, if the moisture content is different, the water content is different, then your properties of that particular soil will be different. So these are the soil index properties. We will discuss about consistency now in detail. So what is soil consistency? Consistency is basically resistance of soils to deformation. If you try to deform a soil by applying like shear load, in this case, one force is applied in this direction, another force is applied in this direction. So this is called shearing force. So in this case, you can see that there will be some resistance at this surface. Where there is a contact, there will be resistance, and this resistance will, if it is greater, then it will take a lot of shear force to slide these two boxes across each other. But if the resistance over here is small, then it will take probably less force for you to slide these boxes past each other. So the resistance available at this surface is basically the shearing resistance. So in case of soil, because the shear strength or shear resistance is the primary resistance which you got, which prevents the deformation or rupture of a soil. So consistency is defined is this resistance, the resistance of soil towards deformation. If you take a sand in your hand and just pinch it, it will give you some resistance. So if you take water, it will not give you any resistance. So this small resistance which is offered by this piece of sand, that is basically its consistency. So consistency of non-cohesive soil depend primarily on the particle shape and size. If you have non-cohesive soil like sands and gravels, in this case their particle shape and size, it will affect the consistency. If the particle shape is large, if the particle size is large and the particle shape is angular, then it will have greater consistency compared to if the particle size is small and the particle shape is more rounder, then it will have less consistency, which means that it will have less resistance to deformation. That soil can be easily deformed. So in case of non-cohesive soil like sands and gravel, it is particle shape and particle size distribution, which basically tells you that if a soil is going to have a greater consistency, that is greater resistance towards deformation, or less consistency or less resistance towards deformation. While in cohesive soil like clays, okay, the consistency primarily depends on amount of moisture content in soil. You may have observed that in case of clay soil, if you put water in it, you can easily mold it, you can easily play around with that, you can even make some toys, some kitchen utensils with that, some pots, etc. So if you increase the moisture content of a clay, its resistance to deformation reduces. If you keep on increasing, it will become mud and it will start flowing. Okay, but if you keep on reducing the moisture content or the water content of clay soil or cohesive soil, then in that case it will become stronger and stronger, and if it is completely dry, you see, then even clay soil offers a lot of resistance to deformation. If you take a lump of a clay which is dried and try to break it, it will give you a lot of resistance. But if the moment you put it in water, it will be very easy to squash in your hand, and you can easily squash it, you can easily break it, etc. So in cohesive soil, the consistency, which is the resistance to deformation, primarily depends on the moisture content or the water content. The more is the water, the less will be the consistency. Okay, so who was to discover this? A Swedish agriculture engineer named Albert Atterberg. So Sir Albert Atterberg basically discovered that the physical properties of soil are considerably influenced by the amount of water present in them, and consistency of the soil also changes with the amount of water. So he saw that if you put a lot of water in a soil and then apply load on that, a stress strain curve will be very flat, which means that there is no stress over here, there is only strain or deformation in the soil. So it means it is not taking any load. But if you keep on reducing its moisture content, you will see a stress strain curve will be more steeper and steeper. So if you reduce the moisture content of a particular soil, it is going to affect its shear strength behavior from having virtually no shear strength to some shear strength while the moisture content is reduced. But if you reduce the moisture content further, then you can see the stress strain behavior will be more dominant and there will be more shear stress resistance over here for a particular amount of strain. Okay, for example, for this much amount of strain over here, it is giving you this much amount of stress. But if you take it on this graph over here, where the moisture content is further less, you can see it can take even a lot more stress, almost twice of this, okay, because the moisture content of this sample is more and the moisture content of this sample is less. This is the same soil. The only thing different in all these three cases is there is more water over here, there is lesser water over here, and then further lesser water over here. So we are keeping on reducing the moisture or the water, and the shear strength is increasing. So it's clearly indicating that consistency or the resistance to deformation is dependent on amount of moisture present in a particular soil. So what Sir Atterberg did, although of course human observed this behavior long ago, maybe 5,000 years ago, people may have noticed this, that if you put water in a clay soil, it becomes very playable, very easy to mold, with zero shear strength, etc. But the moment you dry it, it becomes stronger. So there must be something. So Sir Atterberg, what he did, Albert Atterberg, that he divided it into 4 states based on the moisture present, and those states were called liquid state, in which the soil was in liquid state, plastic state, in which it is in plastic, semi-solid state, and then solid state. So he said if you put a lot of water in a sample, then in that case it will be in liquid state. Okay, obviously we'll have to determine later on that what is the liquid state, how much water we will need, but for now let's say we put just a lot of water in it. So it will become liquid state, but if you keep on drying it, it will reach a point that will become plastic. If you further keep on drying it, it will reach the semi-solid, and in the end the soil will become completely solid. So it all depends on amount of water content present in a given soil. So that means that if you put a lot of water in a soil, initially it will be liquid state, but if you keep on reducing its moisture content, it will turn into a plastic. So you can see over here a soil is flowing over here, like because there is a lot of moisture content of this soil, so it is just flowing, and this is called the liquid state. But from plastic to solid state, when it changes from plastic to solid, in plastic there will be no cracks in it, but if it is semi-solid state, there will be cracks in this soil while you are molding it. But in solid state, the moisture content will be very less and it will be much more stronger. So if you keep on reducing the moisture of a particular soil, the soil state will change from one to other, and these are called the Atterberg limits. So based on these states, he gave some limits as well. So what are the limits? The limits are the boundaries between two states. The boundary, if you have soil with a lot of moisture and you keep on drying it, the boundary or the moisture content at which it will change from liquid to plastic, that will be known as liquid limit. Okay, because over here the liquid behavior is limiting. If something is limiting, it means it is going to vanish, or it is diminishing, or it is ending. So liquid limit means that the liquid state is going to limit over here. Beyond this point, it will not be liquid, but it will be the next state. Okay, so that's why it is called liquid limit, because this is the point after which if you further dry, the soil will be no more liquid soil. So it is the limit of the liquid state. So it is called liquid limit. Then from liquid, after liquid limit, the soil will change into a plastic state. Okay, and if you keep on further reducing, it will go into the plastic limit, and then further reduce it, will go to semi-solid state, and then if you further reduce it, it will reach to the solid state. So first discuss the liquid limit. When we mix fine grained soil like clay with large quantities of water, okay, the soil will turn into a liquid state, and it will have virtually no shear strength, so it will start flowing. Something which has no shear strength like water, etc., it flows. It has no resistance to shear. So everything which is solid is because of the shear strength. If something has a shear strength, it will be solid. But if it does not have any shear strength like water or liquids, then it will flow. So if something is flowing, it means that it has zero shear strength. So when you add a lot of water to a particular soil, then it will start flowing and to be in the liquid state. So what we do if we start drying it, okay, if it is left in the sun and it is started to dry, okay, so if this soil is left in the sun rays are striking it and reducing the water content, so there will be a point where the moisture content will be reduced so much that it will start developing resistance to shear, okay, from totally solid over here to having some resistance to shear, like you can see around these edges. Then in this state the soil will be known as at plastic state. So if the soil possesses no shear strength to a point where it starts producing infinitesimal, very small amount of shear, that point will be known as the liquid state, liquid limit state, where the liquid limit has ended and the soil has started to develop the plastic behavior. So the point where it is transiting from having zero shear strength to a very minimum shear strength, this will be the point which will be known as a liquid limit. If you further reduce the moisture content, the soil will be no more liquid at this point. So it will go into the plastic state after that. So now when the plastic limit is going to end. So in plastic state, the soil can be easily molded. Like you can see over here, you've got this thread made of clay soil, okay. But if you further reduce the moisture content of this soil, if you keep on reducing it from this state, if you further keep on reducing the moisture content, you will reach a point where upon making the thread from this soil, it will start developing cracks. Now this will be the point from which the soil is changing from plastic to solid state. So this is the limit of plastic state. If you further reduce the moisture content, then the soil will be no more in the plastic state because it has started to crumble, it has started to develop cracks. So at this point we will know that the moisture content has reached the plastic limit of the soil, okay. So the plasticity or the plastic behavior is almost limiting at that point, okay. If you go beyond this point, if you further reduce the moisture beyond this point, then the soil will be no more plastic, but if you try to mold it, it will start develop cracks. So it is going to be in a semi-solid state. So let's say that we have reduced the moisture content further and we are now in the semi-solid state. So in semi-solid state, the soil remains fully saturated still at this point, and if you reduce the moisture content, the volume of the soil will reduce with equal amount up to this point, okay. So starting with the liquid limit and up to semi-solid state, all the soil is fully saturated, which means all the voids are full of moisture, of water. There are no air voids over here, okay. So if you are reducing the amount of water, it means they are reducing the volume of the soil sample, okay. So up to this point, up to semi-solid state, by reducing the moisture content, not only the state will be changed, but the volume of the soil will also be changed, okay, because the soil is fully saturated. So if you have fully saturated soil, the total volume is equal to what? Volume of solids plus volume of water, because all of the voids will be filled with water. So volume of water or volume of voids will be same. So the total volume will be equal to volume of voids plus volume of solids, okay. But because we know that volume of voids is volume of water if the soil is fully saturated, so the total volume will be equal to this. So It means that if you are reducing volume of, if you are drying the soil, you are reducing the volume of water. So if this is reduced, then the total volume is also reduced as well. So this will be the case of fully saturated soil, because the soil is fully saturated at this point, but if you further reduce the moisture content beyond this semi-solid state, there will be a point where further reducing the moisture or the water, the volume of the sample will not reduce. Okay, because the soil is no more fully saturated. So if you are reducing the volume of water, the volume of the sample will not be reduced, because this is the point beyond which changing the moisture content will not change the volume. So this limit will be known as shrinkage limit. Okay, which means that if you reduce the moisture content further, the soil will not shrink further, the volume will not change. So that will be known as shrinkage limit. So we can plot it on a graph like over here as well. If you plot moisture content and change in volume over here, then you can see in liquid state, while you're reducing the amount of moisture content, the moisture content is plotted over here, so it is increasing in this direction. Okay, so obviously if you are going in this direction, it is reducing. So at this point you can see from coming from here to here, the volume of the sample has reduced by that much amount. Okay, so if you are coming from here to here, so that much volume has changed. Okay, so but in case of plastic, further volume, semi-solid, further volume reduce. But if you reduce the shrinkage limit, which is over here, if you further reduce the moisture content, the volume will not reduce. Okay, the volume will not reduce, the volume will remain constant at this point. So if you can see over here, if you further reduce the moisture content, the volume line will be the same. For any amount of moisture, your volume, total volume, which is volume of solids plus volume of voids, this remains same. While over here you can see, while you are reducing the moisture, the volume was also reducing. Okay, you can see the volume over here is this much and the volume over here is this much. But over here the lines becomes constant. So the point at which further reducing the moisture content will not reduce the volume, that point will be known as shrinkage limit. Okay, so there all the limits are represented over here, like liquid limit is here, plastic limit is here, and shrinkage limit is here. So liquid limit is a limit from which the soil will change from liquid to plastic, and plastic limit is a limit from which the soil will change from plastic to semi-solid, and shrinkage limit is a limit at which the soil will change from semi-solid to a solid state. Further moving on, why this is important. Okay, so few points to ponder over here. We clearly indicated over here that decreasing in moisture content of the soil, its volume will be also decreased. Okay, so that's why Atterberg limits are very important to tell you if in particular state, if you get a soil in a particular state, if its moisture content is reduced, will it affect the soil? In many cases you have seen that you place some mortar or some soil with very high moisture content, and when it becomes dry, it develops cracks, because with reducing the moisture, the volume of that thing has reduced as well, because it was in liquid state while you are placing. Even in case of cement, if you are putting too much water in it and place it like a slurry, you will see when it dries, it will develop cracks. Okay, so it is very important to know that if you are placing a soil, if it is in liquid limit, you should know that it will change its volume a lot upon drying. Okay, so we know that how the volume changes will occur in particular soil, and if there will be any volume changes in a soil, like if your soil is in semi-solid state, you should not worry a lot about the volume change, or if it is in solid state. But if your solid is in plastic or liquid state, you know that if because of anything it becomes dry tomorrow in a dry season, its volume will reduce. So if you have constructed a building on it and its volume reduces, obviously it will reduction in volume will means the settlement, so which will not be a very good outcome. So that is very important thing. We also demonstrated that below shrinkage limit, the volume of soil mass remains constant. Okay, so if you go beyond shrinkage limit, there will be no further volume changes in a soil. We also knew that all these limits are in percentage of water. So you can have a very basic measure, which is very important in many engineering problem. Okay, so you will know the moisture content as well from these limits, that if the moisture content is provided to you, like I have a soil and the moisture content is 25%, so I can go and check the limits of that soil and see that if the moisture content is 25% naturally in the ground, so in which state this soil is it in plastic state, semi-solid state, or liquid state, by checking those limits. So it is also very important. We clearly observed over here that the volume and shear behavior is greatly dependent on these limits. Okay, because you can see that in case of semi-solid state, the shear resistance is a lot, and solid state as well. In plastic state, for the same soil, in the liquid state, the shear resistance is less. And similarly, if the soil is in semi-solid or solid state, the volume changes in this soil will be less. But if the same soil is in liquid or plastic state, the volume changes in this soil will be a lot. Okay, so these limits will be used for classification later on for the fine grained soil. They are used by various standards like Unified Soil Classification System, like ASTO, etc. They have used these limits to classify, to put the soil in different types and different groups based on these limits. So these are very important to know if you are going to do a classification of the soil at a particular site. In next class, we will be discussing about determination of liquid and plastic limit, and then shrinkage limit. The device for determination is available in the laboratory, and you will be doing some experiment later on in the laboratory as well using this equipment, and you will determine the liquid limit, the plastic limit, and shrinkage limit for a given soil. So hopefully it was a fruitful discussion today. If you have any question, you can leave it in the remarks or later on the portal. Thank you very much for listening. Take care.